Hey, ham radio and vector mathematics, specifically cross product fans. This is KD0FNR. I'm getting a little bit of time. I'm away from the rig this week, so I'm getting a little bit of time to look over some of the things I've built over the last year. And I came across this post where we wanted to calculate the skip of radio signals off the ionosphere as accurately as we could. But there aren't that many ionosondes around. So one of the things we needed to do was be able to estimate when an ionosonde says how high the F2 layer is, how far that ionosonde is from the path of the radio signal for our QSO. So for example, here you see this radio signal starting out around San Francisco, cruising over the Earth, landing over in probably Sweden. And the ionosonde that can give us data about the middle is over here by the Great Lakes. And then the question is, when it says that the F2 layer is a certain height right there, how much do we factor that in? So in the first guess at that is, well, look at the distance from the ionosonde to the path of the QSO signal. But how do we do that? And it turns out that cross products that we learned in high school are the answer. And so there's a post on this, but I'm going to also walk you through. And because there's some really cool math demos, I think anyway, that I made with CoCalc that are embedded in the post. So first thing we're going to do is we're going to have a sphere, and that's going to represent the Earth. I did study physics, so right off the bat, I'm going to tell you that the Earth in these examples has a radius of 1. That'll be okay, I promise. But here's the sphere, and what I've done is drawn lines from the center of the Earth out to the coordinates of the two QSO stations. So one is in San Francisco, the other one is in Sweden. I can probably figure out a way to line this up so that it looks kind of like the map. But the general idea here is that the purple-ish line is the ionosonde. The two similar colored blue lines are the QSOs, are the stations involved in the QSOs. Great. So now I've got these vectors that point at the 3 points of interest. So that's cool. Okay, what next? Remember, what we want to do is find out the distance between that ionosonde and the path between the two stations. So here's what we're going to do next. We're actually going to use a cross product, not just get assigned one in math class in high school. So if we take a look at this, I used a CoCalc, which is also called Sage Math. You'll see that down there, to calculate the cross product of the two vectors between the QSO stations. So if you remember, the ionosonde was a purple vector, and it's still right there. And if you remember from high school math, when I do a cross product of two vectors, what I get is a third vector that is perpendicular to the first two, and that also defines a plane between the first two vectors. So when I orient it like this, you can see that plane goes to flat. My cross product is at a right angle to the plane, and the plane is between the two stations. Okay, cool. So now I've got a line that is perpendicular to the plane that is defined by the two QSO stations. Kind of cool, fun to look at and spin around, but what's next? We still don't have that distance, right? Okay. So, and also, by the way, I got the math for this off of Stack Overflow. I built the demos to help myself see it and visualize it, but this is definitely someone else's algorithm. Cool. So I've got my plane between my two QSO stations, but what I really want is I want to know where the a line from the ionosonde to the path intersects the path at a right angle. Another thing you may or may not remember from high school geometry is if I've got something like this, and I want to know the shortest distance from the point where the ionosonde is up to the path, I need to find the distance of a perpendicular line, and there's only one. Well, you know, I could go all the way around the Earth the other way, and that's a longer one. But anyway, there's only one short one between the ionosonde and the path, or there could be none. We'll get to that in a second, several seconds. So, I need to find the perpendicular line between the ionosonde and the path of the QSOs. I made a cross product that included the QSOs. That gave me the plane of the QSOs, and it also gave me this vector that was perpendicular to the plane of the QSOs. So now I'm going to steer this around a little more. Remember our first vector, and I'll get there, I thought I had practiced enough. Our first vector was this green one, and that's perpendicular to the plane that contains both the QSO stations. And what I'm going to do is I'm going to take that green vector and do another cross product. That gives, except I'm going to cross product it with the ionosonde vector. And so then this really cool thing happens. The vector from the first cross product is perpendicular to both of the paths of the QSOs and defines a plane. And that means that any plane I draw that contains that first cross product vector is going to be perpendicular to the plane between the two QSOs. So, if I take a cross product between that green vector, the first one, and the ionosonde, that gives me back a vector that's perpendicular to yet another plane, and that plane contains the green vector. So, what I wound up with, the important part about this is the green vector is by definition perpendicular to the plane. And remember that plane between the two stations, it contains our path. And now the new cross product plane also contains a path to the ionosonde. And because they're in the same plane, I have the perpendicular path from the ionosonde to the path of the QSO. And let's see if I can get you where you can see that. But there we go. You see the green plane, that's the two QSO stations. You see the pinkish plane that contains the ionosonde. And that intersection that they make, I promise you, is, and eventually maybe we'll get to see it, is in fact perpendicular. There we go. And so when you take a look at the intersection, there's our right angles. Cool. So now if we look at the edge of that plane, we have a path from the ionosonde that intersects the path at a right angle of the two QSO stations. So we did it, almost. We figured out, we've got a picture of that red path now. Now the last issue is we don't know where that red path is. It's okay, we're going to do one more cross product. So this is so cool. I did so many cross products in high school, never used them, and in one algorithm I'm using 3 of them. So I am very stoked about this. Hopefully you are too. Probably if you're not, we're 9 minutes in now, you're not watching anymore. So me and the last 3 vector math people are going to enjoy the rest of this, I think. Okay, so I have got this extra, the pink plane contains the perpendicular path between the ionosonde and the two QSO stations. I need to know where they intersect. Okay, well let's think this through for just a minute. Our first green vector, that first cross product, that's guaranteed, we know for a fact, because that's the way cross products work, that it is perpendicular to both the QSO stations. Cool. Now, the pink vector, the one that came out when we made a cross product between the ionosonde vector from the center of Earth out to the ionosonde, that pink vector, red vector here sort of, what it is all about is it is perpendicular to the path from the ionosonde to the green vector, and that gives us the perpendicular path, right? Where the ionosonde's path crosses the QSO path. Awesome. Now, what would happen if we cross-producted our green vector and our pink vector? Well, it's a cool thing. Once again, the cross product has to be perpendicular to the two vectors that are in the cross product. And so, and as usual, right when I'm going to talk about the result, I've got this thing pivoted in a way that I can't control it anymore. Here we go. We're going to get there. So, pink vector cross-producted with the green vector right there, and the result has to be perpendicular to both of them. Well, that means that the result, there's only one direction it can go. It can't be in that plane, in the original QSO station plane. It definitely can't be in the ionosonde to the green vector plane. And so that only leaves us one real choice, because it's got to be perpendicular to both those vectors. And the thing that is perpendicular to the green cross product vector and the pink cross product vector is, we're going to get there, I think, maybe. There we go. When we cross product those two, it is going to make a vector, and we're going to do the math and prove it. It's going to make a vector that comes straight up from the intersection of those two vectors and points along the intersection of the pink and the green planes. And please do go to the post and steer these around yourself so you can convince yourself. But we're going to do that cross product now. We're going to take the cross product of the green vector and the pink vector and see where it winds up. So here are the results of that cross product. And there's our green vector down there. There's our pink vector. And you will notice there is this new plane that cross product defined. That's cool. We don't need it right now. What we need to know is, check that out. Ionosphere path is in the ionosonde path is in the pink plane. QSO path is defined by the green plane. They're at right angles to each other, and that black vector goes right along the intersection of the two planes. So what I can do with that black vector, it's in Cartesian coordinates. I can convert it back to spherical coordinates, and at that point I have a latitude and a longitude along the Earth. Then if I want to know, now that I know where the intersection is, I can use a Haversine function. That's something that I've already got. And what a Haversine does is you give it the coordinates of two different points on the sphere, and it calculates the distance between them. And then we get that distance that we were looking for. And so that is it. 3 cross products to get the distance between the point, between a point and a path. One last note. There is the possibility that there could not be a perpendicular line between the point and the path. So, for example, if the point was down here off the, or even near the lower left corner of the picture, below and to the left of that QSO path, if the Ionosonde was, for example, on a ship in the Pacific southwest of San Francisco, we wouldn't be able to make a shortest path that was perpendicular to the, or actually any path between that point and the path between the two stations in the QSO. And so at that point, what you wind up doing is you write a little conditional code that says, hey, if we can't do this, then go ahead and measure the distance from the Ionosonde to the end of the path, and that will be the shortest distance between the Ionosonde and the path. So that's it. For perpendicular distance, you take a cross product of the two stations that are in blue there. That cross product gives you the bold green vector there. You take that vector and you cross product it with the Ionosonde's position vector. That gives you the pink vector here and two planes that are perpendicular to each other. One plane defines the QSO path. The other plane defines the path between the ionosonde and that first cross product. Then we take another cross product, and also that defines where the perpendicular intersection from the ionosonde to the QSO path lives. Then we take one last cross product between the pink vector that we got out of the first cross product, and the green vector, pink out of the second one, green out of the first one. The only place that resulting vector can live and be perpendicular to everything it needs to be perpendicular to is it has to run along the intersection of the two planes. And that gives us the position where the two planes intersect, cast that back to latitude and longitude, and we are off and running. Thanks for all your time. Check out the posts. There's more detail, and you can actually play with the vector products and visualize them yourself. This is KD0 FNR. Have fun. Bye.